Okay, let's look at actually a pretty long involved question that asks us to calculate the equilibrium concentrations of all of these different components in a solution that's actually made up of two different compounds. Okay, methylamine, CH3NH2, and pyridine, C5H5N. So first thing I have to do is write down what the acid-base reactions are going to be for these two substances. Okay, and so let's start out with methylamine, which is CH3NH2, and this is acting as a base, so this can react with water to form the methyl ammonium ion, CH3NH3+, and hydroxide ions. And the Kb for this reaction is about 4.4 times 10 to the negative 4. So to set this up, I'm going to create a little ice box. Right? So the I is the initial, C is the change, E is the equilibrium. So I know that the initial concentration of the methylamine is 0.25. This is going to go down over the course of time by a certain amount x, which means that at equilibrium, this is going to be 0.25 minus x. The water, I really don't care about, so I'm just not even going to bother. And the initial concentrations of the products are both 0, but over the course of time, this is going to go up by a certain amount x, and this is going to go up by a certain amount x. Because of the stoichiometry, they're all in the 1 to 1 to 1 ratio. So then the equilibrium values for these are also going to be just plain x. So now I can write down my expression for Kb, which is the concentrations of the products, right? The methyl ammonium ion times concentration of hydroxide ion divided by the concentration of methylamine. And set this equal to 4.4 times 10 to the negative 4. And now I can use my algebraic expressions. Concentration of each of the products is x, and the concentration of the reactant is 0.25 minus x is equal to 4.4 times 10 to the negative 4. Here I'm going to use a little trick. Because the degree of dissociation is really, really tiny, meaning that the Kb is really, really small, I'm basically going to ignore the x in the denominator, so that instead of having to solve a quadratic equation, I can simplify my life and just kind of isolate the x a little bit more easily. Okay, and so here's what I'm going to do. I'm going to say that 0.25 minus x is approximately the same as 0.25. So then really what I have to solve is x squared over 0.25 is 4.4 times 10 to the negative 4. So now I can solve this for x. So if I work this out, I get a value of about 1.05 times 10 to the negative 2. Now if I go back to what x represents the concentration of this cation, methyl ammonium ion, and it also represents the concentration of hydroxide ion in this reaction, 1.05 times 10 to the negative 2. And then to get the amount of methylamine, I have to subtract that number from the initial quantity, right? 0.25 minus x, 0.25 minus 1.05 times 10 to the negative 2 gives me actually about 0.24. So it's very, very close to the original value of 0.25. Okay, so now let's look at the second part of this problem, which asks us to basically do the same thing, but for pyridine. So here's pyridine. I'm going to add water to it to make the pyridinium ion plus OH minus. And now I'll set up my icebox once again. Oh, the Kb, by the way, for this reaction is a lot smaller, 1.7 times 10 to the negative 9. So now this concentration initially is 0.1. It's going to go down by a certain amount x. So then at equilibrium, this is going to be about 0.1 minus x. Once again, the water I ignore because it's pure liquid. And the initial concentrations of the products are all 0. So these are going to go up by x. So at equilibrium, I'll have x for each of those. And then Kb is going to be concentrations of the products, okay, which are shown here, divided by the concentration of the reactant. And this has to equal 1.7 times 10 to negative 9. So once again, I'll insert my algebraic expressions. So I get x squared over 0.1 minus x equals 1.7 times 10 to negative 9. Make the same assumption that I made before, which is that the x is going to be small in the denominator. So I'm going to replace 0.1 minus x. It's just 0.1. So x squared over 0.1 equals 1.7 times 10 to negative 9, which means that x squared is 1.7 times 10 to negative 10. And if I solve this for x, I get about 1.3 times 10 to negative 5. So once again, if I go back to what x represents, that's the concentration of this pyridinium ion, which is 1.3 times 10 to negative 5. Also represents concentration of hydroxide ion, 1.3 times 10 to negative 5. And the concentration of pyridine is going to be 0.1 minus 1.3 times 10 to negative 5, which is going to be almost exactly 0.1 because that's such a small number. Okay. Now, the question asked, what were the amounts of these different substances, which I listed for you, but you'll notice that there's actually a hydroxide ion here, so that the concentration of OH minus is 1.3 times 10 to negative 5, but I also have hydroxide ions on the previous slide. The concentration of that. And the point is that the concentration of OH minus is a lot larger in the first reaction than it is in the second reaction. So I can basically disregard the second amount for OH minus and say that the true amount of hydroxide is 1.05 times 10 to the negative 2 plus the amount that I was getting from the second reaction, but I'm going to neglect that. And so the final amount of OH minus is really just going to be the one that I get from the first reaction.